Alright, so as we can see, this is the heatsink model. Okay, so first we are going to apply a 10 Newton load from the front face. Alright, so we're only going to apply one point, the center point. Okay, so as you can see, I've already created the center point here. So what we do now is basically we can start to run our simulation. Right, I'll click new study. So static. Okay, so it's just 32. It doesn't matter the name here. Click on OK, and then your material has to be alumina. Okay, so apply an alumina. So once you apply, you close, and then you have to fix the geometry, fixture advisor, fixture geometry. You click the back, meaning the bottom of the heat sink. We are going to fix this as the fixed geometry. Okay, and then our external loads advisor in the top panel, we can click this and we click on force. Okay, once you click on force, we have to select the center. Once you select, you change this 1 to 10 since we are going to work with 10 newtons, and then you click on selected direction, and then since the force is going to enter inside the load, so we select this line here. Okay, so you select this line here, and then you change this to 10 newton. Okay, so now it's ready to run. Click on run this study. Okay, so as you can see, this is the model they've already rendered. Stress, displacement, and strain. You want to have a side-by-side comparison. You click on compare results and you click OK. So this is the side-by-side comparison. You have stress, strain, displacement, mesh. Then we save this image. Okay, we just label it as heat sink 10 newtons front. Okay, so then we exit the comparison and we open up a new file. We exit the comparison, we open up a new file with parts. We will open up the same heat sink file. So we open the heat sink. Alright, so now we have to make a point at the right side, this face here. So what we do is we click on sketch, and then you click on center line. You select this part here, and then you make a line from here to here, and then you click again, you make a point from here to here. You exit, you click on features, you go to reference geometry, you click on point, you click on intersection, and you click these two dotted lines, you'll get intersection point here. You click OK. Okay, so now we can start our simulation. Study statics. Okay, static non-linear test. So you will apply alumina, apply and then close it. And then our fixture advisor, we have to fix the geometry at the bottom. Okay, we fix the geometry, it's the same. Alright, you just change this to first we click the center point of the point here, and then you change this to 10. You click selected, and since you want this to enter, we want the load to enter inside, you click down this line here, and you will see a load direction appear there. And of course you have to change this to 10 newton as well. Okay, so you have it this way. Now you can run the study, so you have to wait for a while. Alright, so you have your rendering here. So of course we have to compare the results, right? So side by side comparison will be generated and you have it here. Okay, so we can always save this image. So I'll save it as heat sink 10 newtons right side. Okay, so I'll save it in downloads, and then the same thing I will do again. Before that I have to exit. Always exit your comparison, and then you open up a new part folder. This is what I do. I use the part, not the assembly. So I opened up the heatsink, the previous heatsink model generated, and now I have to make another center line here, the top face, right? The same procedures. You click on sketch, you click on center line, and you click on the face you want to do. Okay, and then your line, you drag it like this. Okay. You click on center line, and then you do it like this. Okay, you exit features, reference geometry, point, intersection, and then you select the. Alright, so voila, you have your point here. Okay, so you rotate it so that it becomes like the original assignment picture, and now you can start your simulating. Okay, so you apply the material to the alumina, apply, close. Same, you gotta fix your geometry. Okay, alright, so you fix it. Alright, so external loads advisor, your same thing. Now you select your force. No, sorry, it's the wrong selection. You go again, force. You zoom it so that you can see clearly. You click on this. Right, you change it to 10. Then you click on selected direction, and then I choose to click this line because the load is going downwards, right? So I click on this. You can see it's going downwards. I change it to 10 newtons. Okay, so voila, you have it here. So you can run the study. And you compare your results. Okay, so you have this. Alright, and then you save it. Okay, so you exit your comparison. Now we can check we can transfer it so that we can see. So previously I have done for 1 and 5 Newton, front, right, top, front, right, and top. I've prepared this also just to insert. We will insert our images that we have saved, right? So front, insert. Just for easy to compare, we can see what we can infer from this simulation. Alright, and heat sink on the right side, insert, smaller. Okay, alright, so I'm just making it, as you can see, a bit bigger so that we would have a vivid description of the comparison between the values of the stress, strain, and displacement. Okay, so Now we can see, all right, we have done for 1, we've done for 5, and we have done for 10. All right, so if you look at the front side, you can see the values. So if this is a higher value, what we can see is that it is more susceptible to displacement, to deformation, because it has a higher value here, higher stress value here, compared to 5 Newton. Since 5 Newton is a higher value in general, we are applying more load. You can actually see how the strain it actually moves, right? If I show you the comparison of the front side, you can actually see how the strain evolves based on the values of the Von Mises. And through this, it would allow us to select the right materials to use. This is properties of an alumina, right? Okay, so of course we only used 1, 5 and 10 as our parameters, but we can choose to use much higher loads as well. All right. Okay, so thank you very much.